Hi, can you hear me?
Yes, sir.
Okay. Okay, so we can start. So the format of the lectures from now on will be, as I explained on the group, I will be focusing on the easier topics in the first half up to 10:30. It's not a strict time guideline. It can sometimes overextend, or we may end early also. And from 10:30 onwards, we will take slightly harder topics. But in either case, there is not much theory to be taught directly. So the approach I'm going to take is we are going to focus on problems first. And while solving the practice problems, if we encounter some topic which either you have not studied or you may have studied but need some revision, we can briefly learn that topic again. But for the most part, the first priority is to focus on problem solving. And in that also, of course, the first few problems, the first 3-4 problems will be on the easier side, so IOQM style. So their answers will be like numerical 00 to 99 kind of pattern, and remaining problems will be more subjective, long form, like what you'd expect to write for INMO. So it's good to get some practice of both kinds of topics. Okay. And also, I mean, to be honest, I would have liked to share the problem sheet in advance so that you get some time to work it out, so that we are not spending the time in the class for you to attempt the problem. So I'll do that from next week onwards. So next Sunday's problem sheet I will send beforehand only, so that you will get some time to work out the problems. But it's okay. For today, you'll have to sort of do both things together. So I'll give you some time to think, and after that we will discuss the problems. Okay, so out of these, the first three problems, 1, 2, 3, are the easier ones, and 4, 5, 6 are the harder ones. But I put all of that in the same worksheet because quite possible that somebody may finish the easy problems and you can immediately move on to the harder problems. So there is nothing stopping you from doing that. Okay, but we will discuss the problems in the same order as it is given. So we'll start discussing the questions after 10 minutes.
Sir, in the second problem, it is zth root of n, right?
Yes, it is Z root of n. But actually, wait, I'm just checking the second problem. I don't know if there is some calculation mistake. And you can try the problem. It might be some minor error.
Okay, sir.
Let's modify that problem. So instead of 20, just take 1000. That is the only correction.
Sir, y root of 1000, right?
Why is it not 1000, please? Okay, question one, can we discuss? Can you raise your hand if you have got question one already? Okay, I'll wait for some more time. Uh, Actually, this question relies on a property related to this A equal to 2B, which I don't know if everybody has studied. Are you aware of that? A square equal to B into B plus C.
Yes, sir.
Okay.
Yes, sir.
Okay, but I think many others may not be aware, so I think we have to look at that first. Okay, so I don't want to rush into this. As I said, that the first half is going to be for students who need to take some more time to practice the easier concept. So I'm instead of giving you the final answer or whatever, I want to try and motivate you to discover it as much as possible. So with that in mind, to begin with, I'm just mentioning that there is a property which can be discovered. Let's start from there. Suppose ABC is a triangle where it is given that angle A is twice angle B. Okay, so then we want to find some relation between the three sides of the triangle. Okay, which and that relation will be an if and only if condition actually. So whenever that relation is satisfied, we can say that angle A is twice angle B and vice versa. So that is what we would like to discover. So in what we have is, if I call this angle X, then this is 2x. This is all that we know. Okay, so starting from this, I'll give you some time to think that what can we do, what can we explore to get some relations between the sides of the triangle. And there could be multiple solutions for this. Doesn't have to be only one solution. But whatever approach you want to try, you can spend some time on that. And also, by the way, what I'll do is I'll just because I will be sharing my tablet. If somebody wants to take a look at the problem set again, so they will have to wait for that. So instead of that, I'll just post a link to the problem set on the WhatsApp group, so anybody can access that offline also.
So could you please send that on Zoom chat as well?
Okay, sure. Okay. So as a hint to attempt this problem, I would like you to think back to how we prove a different theorem, something that we all must have done at some point, which is the angle bisector theorem, right? So the this is something that we know. If the consider the angle bisectors, then BD upon DC is equal to BA upon DC. So try to recall how you approach this proof and try to see if some similar theme can be applied in this problem also. That is one approach, not necessarily the only approach, but certainly one approach. Yes, Raghav, do you already know the property or
Yes, like I think I have an idea similar to what you did.
okay, I will just give some time for others. This is the best part. After the exam is over, there is no time pressure. We can take as much time as we want to explore the answer. Even I'm not in a rush to reveal the solution. So, in fact, in that process, we end up discovering more like multiple solutions. Okay, so what can we do in the angle bisector theorem case that is applicable here? Yes, Raghav?
Yes, so after you take the angle bisector, you can see that angle DA in this case, like if you take the angle bisector, the first figure,
Mm-hmm.
and
So
you
that draw the
label,
angle bisector? Okay.
yes, sir. And if
Okay.
you label the point D, then you can see that DAB is equal to A
Hmm.
is equal to ABD. So ABD is an isosceles triangle.
Yes,
And also you can see that angle ADC is equal to angle A.
yes, correct.
So you get two similar triangles.
Yes, so whenever we have, in fact, whenever we have this kind of pattern, right, this is something that is worth noting. Whenever you have this kind of alternate angles, right, this angle over here is equal to this angle over here, and this angle C is common. So immediately you see there is a like a mirror image kind of effect that and triangle CAD will be similar to triangle CBA. Okay. So how do we use that?
Yes, so you get that like AD upon AC is equal to AB upon BC.
Maybe. Okay.
But now we know that AD is equal to BD.
Yes, so we can write this as BD upon AC.
Yeah. And so after like so BD is going to be 1 second. I guess my figures are bit different. Yeah, so BD would be AC upon B plus C by angle bisector theorem.
Yes,
And then AC is going to be equal to B.
yes.
And
So AC is B, AB and AC can be written as C and A. So basically what we have is, if we write everything together, so AC upon B times B plus C is equal to C by A.
yes, sir.
Okay,
Then
and
you
here,
get A square is equal to B times B plus C.
okay, A square equal to B into B plus C.
So we can
So-
also use the length of the angle bisector formula. It is much lengthier calculation, but I am giving
Mhm. Okay, yeah, because we AD we already expressed in terms of BD, that is also one certainly one possible. What is the formula for angle bisector? I forgot.
Sir, AD square is BC into 1 minus A square by B plus C the whole square.
Sorry, can you repeat that?
BC into
Hmm.
1 minus A square
Okay,
by B plus C the whole square. No, sir, only A square has the denominator, not 1.
oh. BC into 1 minus A square upon B plus C the whole square. Like this?
Yes, sir.
Oh, okay. Yeah, this can also certainly lead to the same conclusion. Any other approach that we can think of? First, did you understand everybody this angle bisector approach? Is that fine?
So we will be taking triangles ACD and BCD, right?
Mm-hmm.
So the
AC,
ratios will be
ACD and BCD, but look at the correspondence because it's a mirror image kind of triangle. Right? So this angle 2x is going from here to the opposite side. So the order of the vertices is anti-clockwise versus clockwise. So the
so the
angle.
order.
Yeah, go ahead.
So the order will be
What I've written here, right? CAD and CBA, right? Because angle C is common, and angle D, which is this 2x over here, is equal to the full angle A, right? Which is 2x.
yes, sir. So the ratios will be AC upon BC is equal to CD
Yes.
upon AC is
Yes.
equal to AD upon AB, right?
Correct. So
And
I
that is
mean,
1.
yes, correct.
Okay.
Yeah, I mean, only difference is here I think Raghav was showing the ratio. I mean, when we wrote AD upon AC, we are actually comparing AD upon AC in the same triangle. So AD upon AC over here should be equal to BA upon BC in the other triangle.
But
By the
I
way,
had
I
a
think
similar approach to Raghav, like very
Yeah.
similar.
okay.
Like what he did inside, we can just replicate it outside.
Yes.
Like
So
if we start with triangle ACD, even that is a x2x triangle, so you just take it outside.
So Nick, can you tell me what is the
Sir,
construction?
can you
which
just
was made?
scroll up a bit to
Okay.
the Raghav to Raghav. So like
Okay.
if we are given with triangle ACD,
Mm-hmm.
we observe that in this also it's the 1:2 angle ratio.
Mm-hmm.
Then we move on to triangle ABC. Like we replicate that figure outside. So like that's the similar method, but the ratios we get to be same only.
I know what you mean. So basically, actually that is the idea which I was trying to indicate, because that is the one angle bisector theorem proof that we all know, that we draw the bigger isosceles triangle, like this kind of a thing. So something similar I was trying to hint for this also. So what if we do this, that we know this is 2x and this is x. So why don't we construct this kind of a triangle outside? So basically this line will be parallel to the angle bisector. Okay, so we get some kind of BPT actually. So, but yeah, basically the calculation will be very similar, because in this case we'll get, what happens is that because this angle is x and this line is parallel to this line, so the alternate angles also mean that this angle is x. So, I think this triangle becomes isosceles, etc. But anyway, it doesn't matter. So there is one more approach which I was thinking about just now. What if somebody did not think about this construction approach? What else can they do? So I mean, it occurs to me that this approach should also work. Why don't we just do it directly through relating the angles? Because what I know is angle A is twice angle B, right? So if we try to use that information directly, we should be able to write something like this. So firstly, I have to translate the angles into sides. So I can take the cosine for that. So basically, cosine of angle A is cosine of twice angle B. That's what we are saying here. And now both left hand side and right hand side can be written in terms of the sides of the triangle, because by cosine rule, the first is nothing but b square plus c square minus a square upon twice bc. And cos 2b is 2 times cos square b minus 1. And again, cos b can be written in terms of the, so a square plus c square minus b square upon 2ac whole square minus. So now we are left with purely some information in terms of the sides of the triangle. So with simplification, ideally it should come back to the same answer, a square equal to b into b plus c, but I think it will be good exercise to verify. So in fact, I will suggest this as a homework for you, as just as a to train your ability to do calculations without making mistakes. That see if you can simplify this also down to this, or for some reason it doesn't happen, we'll come to it. Okay, but so this was the basis of this question. What was that first question? So now that is given to us, that a equal to twice angle b. So the sides are also integers. So now we have to look at this as a Diophantine equation. That is an equation considering positive integer solutions. Okay? So a square equal to b into b plus c. The way you can approach this problem, because we are given all the sides are less than 10 and they are integers, right? So effectively, if you think about it, how b and b plus c are just two factors of a square. So in general, if a square can be factored as p times q, where one is smaller than the other, right? Let's say p less than q, then we can say that the smaller one is b and the larger one is b plus c, right? But do you see where a problem can arise if we try to do this? For example, if somebody says, let's take a equal to 8, okay? So 8 square is 64, which we can factorize as, let's say, 4 times 16. So as per that logic, b is 4, b plus c is 16. So c is 12. So what's the
triangle
problem?
inequality may not hold.
Yes, the triangle inequality is the problem, because it could be that in particular if the b and b plus c are too far apart, right? I mean that will cause a distortion of the triangle. So we need some additional condition to be verified also. That basically we need to check all the three conditions: a plus b greater than c, b plus c greater than a, and c plus a greater than b. But out of those, we'll see that some of them are kind of redundant, because see, by design, we are always going to take the Q larger than P. Okay, so the B plus C is always going to be the larger of the two factors. So therefore, B plus C will be always greater than A, right? And B will always be less than A. So this is kind of given to us that this will be true. So we don't have to check this explicitly. Okay. Similarly, do you see that A plus B greater than C? Will this be always true? No, sorry, this one. This will also always be true, right? Because we already have A greater than B. So obviously C plus A will also be greater than B. So this will also be true. But so the only condition to be checked is whether A plus B less than C is happening or not. Okay. So if we, let's say we just make a table of the possible values of A, and I don't know if this is the most efficient approach or not, but just to consider. So I'll make a table of A square, the factors B in B plus C, the corresponding value of C, and what we want to check is whether A plus B greater than C holds true or not. Okay. So we can just go ahead and make this table for values from 1 to 9. So I mean 1 is the trivial case, so we can ignore that. And in fact, you will observe that if it's a prime number, right? If you take a prime number like 2, so then by default, what will happen is that there is only one non-trivial factorization possible, which is 1 and 4. And that always leaves you with the situation where this A plus B greater than C condition is not satisfied. Okay. In fact, here you will get equality, but equality is not enough. We need strict inequality, right? So in this way, you can proceed to check all up to the 9 numbers. And out of those, I mean, again, we can be efficient in eliminating cases. Like for example, as I said, prime numbers can be straight away discarded. And among the rest, you may find a valid solution. So does anybody have a valid solution?
Yes, sir.
Yes, sir. Tell me.
Sir, it holds for A is equal to 6, B is equal to 4, C is equal to 5.
Yes. So, and that is the only solution, right? In the
Yes,
entire
sir.
set. So A is equal to 6, so 36. 36 can be factored as 4 into 9. So that if B plus C is 9, C is 5. And in this case, A plus B greater than C is satisfied. So 6, 4, 5 is the only triangle which satisfies this condition. Okay, so the answer is the perimeter, which is 15. Okay, so I hope everybody followed the rest of the solution. It was all based on that property. That
Sir, how
is
did you state that A plus C is greater than B? How did you get that?
A plus C is greater than B because see, when we are factorizing A square as B into B plus C, right? Whenever a number is factored this way, one number will be smaller than the geometric mean and one will be the greater than the geometric mean, right? So
Yes.
here B being the smaller number, so B will be less than A. So if B is already less than A, adding C will make the this even larger, right? We already have A greater than B, so we are adding another C to the left side. Okay. Any other approaches that you want to suggest? But I don't think there's a lot of flexibility here apart from the whatever we did right now. Okay, so then question 2. As I said, just take this as 1000 instead of 10. Even after that, I'm not sure about calculations, but let's see. So
Actually, I'm getting some kind of contradiction in the second one.
even with 1000.
Yes, sir. Like I've sent you in chat right now.
Oh,
What
okay. I
contradiction
have
I'm
not.
getting.
Actually, let's drop the condition that x, y, z are positive integers. Does that solve the problem?
Yes, sir. Maybe the maybe it will solve.
I'll have to check also. Anyway,
Actually, even in the first question of 20, I was getting a contradiction.
no, 20 was I remember some calculation mistake I must have done. Okay, anyway, I'll I mean the numerical calculation don't matter that much, but I just want to indicate the approach that you can follow to solve a question like this. So so what is given to us is that xy plus yz. Okay. So this is the first information given to us, and the second one is in fact, let me take this.
Shall we consider x, y, z positive, or they can be any integers?
Let them be any real numbers for that matter for now, okay? Because even I'm not sure. I mean, I don't even know whether we require to use them being positive or not. That information might not be required also. So let me just drop that.
Okay.
And in order to find out what should be the real value, let's just fix this problem. So I'll call this as m. So I mean, originally I said m equal to 20. Now I'm saying m equal to 1000. But even then I'm not sure. So let me just call it n. So now we have to find the value of n in terms of m. N and m are very similar sounding, so let me call this k. Okay, so we have to find n in terms of k. So can somebody tell us how to get started with this?
So what I did was I raised all of them to the power x, y, z.
Yes. Okay. So let's first rewrite this in terms of, like, instead of using the radical sign, you can write this as k raised to 1 by y. Okay. So first, even before we begin, do you see what is the connection between the information given at the top and the exponents over here? So they are clearly reciprocals. And so if you want to relate them, either we have to translate this information in terms of reciprocals, or we have to put the reciprocals in terms of the quantities. Okay, so that is the main observation that we need to look at. So yeah, either we can divide this equation by x, y, z. So we'll get, yeah, I think that is that, because I want to divide by x, y, z. That is why I must have given them as positive. But anyway, so if we divide this by x by z, we get 1 by z plus 1 by x equal to 2 by y. Or instead of that, if we multiply this, no, so raise everything by x by z over here, as what Arnav was saying. So then we'll have this whole thing raised to x y z. Okay. And so what will be left with is 10 raised to yz equal to k raised to xz equal to n raised to xy. Okay. And now again, either way, we are going to be in the same situation where we have basically 3 objects over here. Okay. And we can rename them for convenience as some, we can call this A, B, and C. And the information given to us is that A plus C equal to twice B. Okay. So we are kind of, see, it's a change of variables. We are no longer talking in terms of x, y, z, where we can talk in terms of A, B, C. Okay. Same thing can be done if you did this also. If you divide the original equation by x, y, z, you will land up with the same situation. So 10 raised to A equal to k raised to B equal to 10 raised to B, where A plus C is equal to B. And we want to find the value of n. So the difficulty seems to be here that here the values ABC are as powers of some quantities, and here they are not as powers. Here they are like normal numbers. So how to connect them to each other, we have to think about. And in fact, here I am writing this as one single equation, but in fact we are given 2 separate pieces of information, right? 10 raised to A equal to n raised to C, and k raised to B equal to n raised to C. So the idea is, can we use these 2 parts in some way to relate, I mean, bring ABC all down, basically, in some sense. That's what we are saying, right? And what is the function that can be used to pull down the exponent that way?
Logarithm.
Log, right? So if you just take the log of both sides, and we can take log with respect to any suitable base, but What do you think is a good base to choose here?
10.
10 or n? I'm not sure actually.
I had thought of converting all kn in terms of 10 raised to t and 10 raised to something and then get some equations in that.
Okay, so what you're saying is let k be equal to 10 raised to some other value, let's
Yes.
say this way.
Yes, and same with n.
Yeah, we can do that actually. So I mean, in the most general case, even this 10 can be replaced with some number. So let's say k instead of here in j. So j raised to a equal to n raised to c and k raised to b equal to n raised to. So what you're saying is let j equal to 10 raised to some alpha and k is equal to 10 raised to some beta. Let's just go with this for now. I'm not sure whether this is the best approach or not, but let's see. So we'll get 10 raised to alpha into a equal to n raised to c from the first equation, and 10 raised to beta into b equal to n raised to c from the second equation. Okay, what do we do next? See, we are interested in somehow we have to find a plus c. So a has to be brought down. So let's take the log of both sides with base 10. So the LHS will become alpha into a equal to log n raised to c to the base 10. And here we'll get beta into b is equal to log to base 10. Okay. And if we just take alpha to the other side, okay, so adding the two, we'll get sorry. I want a plus c equal to 2b, not this. Okay, so I'm not sure whether this was the approach which you mentioned or not, but let me just outline what I was thinking. So the way I was looking at the problem is that a plus c equal to 2b. So let's just write a, b, c themselves as logarithms of some quantities, which we can do directly from these equations, right? So from here I can say a is nothing but log of n raised to c to the base j, right? And c is nothing but let's say we'll leave c as it on its own, and b is log of k raised to so this is the equation I'm writing. Okay, do you follow how this is coming from? Because to find a in terms of log of j, I'm using the first equation, right? If I take the first equation and take the log to the base j, I'll get this quantity. And the second equation, if I take the log to the base k, I'll get this quantity. Okay. So now the advantage is that the only variables that are left are n and c. Everything else is eliminated. Okay. And now you'll see that even c is going to get eliminated. Do you see how? Because the c is there as an exponent everywhere, right? So what will happen is that we can pull down the
C
c.
times log
Yeah,
j
so
log n.
c will come down as a coefficient. So this will be c times log of n to the base j plus c equal to 2 times c log of n to the base k. Okay, and so cancelling c, we will get an equation which is purely in terms of n. So log of n to the base j plus 1 is equal to log of n to the base k. Now, depending on what are the values of j and k, I mean, there are multiple ways to solve this. One idea is, so that is where I thought that when I took 10 and 1000, right, I solved that problem. So if I put j is 10 and k is 1000, so I thought that that will lead to a clean solution, but now I'm not sure. Because now what I can do is log 1000 itself can be written as log of n to the base 10 upon log of 1000 to the base 10. Okay. So this is nothing but 1 by 3 of log n. So now basically this is the only variable left in both places and I can find the answer. But does that work, or I don't know if there is some issue with that, or now you are saying that that is also leading to some contradiction.
If X, Y, Z are positive, then I think that does not work. But
Okay, fine. Okay, then that might be the issue there. So now what we'll get is 2 by 3 log of 10 to the base n is equal to -1. So n is equal to 10 raised to -3 by 2. Yeah, I mean, anyway, the answer is not very nice even in this case, but doesn't matter. I mean, the point was to show the algebraic calculations. So, yeah, I hope that the couple of things that you're able to learn from this example. So the first thing is how to connect the information, that the equations originally given, if you see, they seem very different from each other. So the information given in terms of x, y, z and the powers, how to connect that was not clear. So through the division or multiplication by x, y, z, we first got them to the same level. Still, after we translate everything in terms of ABC, the problem still remained that half of the data was given as exponents and half of the data was given as simple coefficients. So we need to connect those together. So both exponentiation and logarithm, they are both good functions to do this kind of translation. And even in doing that, if you observe how I approach this question here, I looked at the fact that a plus c equal to 2b was given, and term by term we translated everything into logarithm, keeping in mind that we have to find n finally. So we expressed everything in terms of log of n in some way. And then this c getting cancelled was just a happy coincidence because the question was designed that way. It could be that in some other case the c doesn't get cancelled so easily and this question becomes even harder to solve, but thankfully that was not the case. Okay. So yeah, I mean, doing all of this in the time limit in PRMO can be challenging, but with time and like practice, you can quickly see these ideas. Okay, and question 3. Does anybody have an answer for question 3?
yes, sir.
So what is the final answer?
Sir, I'm getting 5.
5. Okay. This is actually a easy problem in a way if you are aware of general set notation and some basic combinatorics. So I'll give some time for others to think about this problem also, because I don't want to reveal the approach. But does everybody think of the smaller, forget the 10 elements. Can you think of just a smaller set of like representative example? What is happening here? There are sets where if you take any 2 sets at a time, they have a common element, but three sets together will never have a common element. So do you see a very simple example of, let's say we have numbers like 1, 2, 3. then the first set can contain the numbers 1 and 2. The second set can contain numbers 2 and 3. And the third set can contain the numbers 1 and 3. Right? So this kind of example, just to illustrate the concept, right? Something like this. In fact, I mean, this is the typical Venn diagram that we draw. So what if we have the numbers like this, 1, 2, and 3 here, and the middle is empty. So there is nothing in middle. Okay, so do you see this as an example of where any two pairs of set will have common elements, but all of them three together don't have any common elements. So this is what's happening with three sets. The question is just extending that to more elements, more sets. So think along these lines. I'll give you some more time to attempt this question. One more aid that can be used to do if you are doing any kind of trial and error, right? How do we represent this information conveniently? That there are some elements in some sets and not in others. So here is one way to depict this in terms of some like a tabular format. That what you can do is let the first row be all the elements. So these are the 10 elements of your original set. Okay. And now whatever the sets you want to define, A1, A2, A3, etc. Okay. So if you want to put element 1 in set A1, you can just put a tick or any mark over here. You can write a tick or a 1, whatever. So like that you can just tick wherever you think you want to put the elements and quickly do the trial. So here what I've ticked is basically the same pattern which I was showing earlier, that each set contains exactly 2 elements, but all the 3 sets together, there is no common element. Okay, so we want to evolve this kind of pattern. Of course, the important thing is that here we are asked to find what is the largest possible value of n. So we want to include as many sets as possible over here. As Arnav already mentioned, the answer is 5. So the question is, what will happen if you have more than 5 sets? Suppose we had 6 sets like this, A1, A2, A3 up to A6. So I again don't want anybody to reveal the answer, but just think about what could be the issue if we have 6 such A1 to A6 sets. Then and we try to do this kind of tick marks. The 2 conditions we have to keep in mind: any 2 sets at a time, their intersection should not be empty. Okay. And any 3 sets at a time, their intersection should always be empty. So that is the question we have to figure out.
So I think I got it.
Okay, you just wait for a few minutes. Yes, Shreya.
Sir, I tried it by trial and error.
Okay, so what is the answer you are getting?
5.
Right, but for six sets, why can it not happen? Because we want to find a maximal possible answer, right? Largest possible value of n. So if somebody can come up with the answer arrangement with even 6 sets, then the answer will not be 5. Yes, Anushka.
So I haven't found out the problem, but I've got an idea. So
Okay.
let us just consider the first 4 sets for now.
Okay.
So we see that the first element cannot come in A4. So we put a cross there. The second element also cannot come in A4. And the third element will also not come in A4.
Okay, but see the difficulty with that approach is that, I mean, here I just gave one example. It's not compulsory that you have to do the initial assignment this way, right? Somebody can do the assignment in a completely different way. So how can we come up with a logic which will work no matter how we start our assignment?
So when I did it like this, I found that for if we just select like 2 elements in A1, 2 elements in A2, and 2 elements in A3, so we get that in A4 none of the 3 elements will work. So and then now if we do it like one element in A1, one element in A2, and one element in A3, we will get that we'll get that in A4 we'll have to have all of them.
Okay. No, I mean, I understand your approach, but I still have the same problem that is it really covering all the possible cases? Because somebody can say, I want to start by assigning from the 10th, I mean, the last elements first somehow. So how do we ensure our approach is robust to all such possible ideas? So here is one question maybe I'd like to ask. Can you first try to find out for any element in S? This is the question. So for any element I in S, okay, at most how many sets can I belong to? Okay, does everybody understand the question that how many different sets can every element in S belong to? Can some element belong to three sets? Suppose there is a, for example, say one, if there are three ticks, will that be allowed or will that be a problem?
That won't be possible because A2, A4, A5 will have a common element.
Correct. Okay, does everybody understand this? That we cannot have three ticks, so at most two. So the answer is at most two. Okay, so every element can be a part of at most two distinct sets. That is the first thing that we have to observe. Secondly, the other way around, see, if that is true, that every element belongs to at most two sets, and if you consider any two sets AI and AJ, okay, so AI intersection AJ is not empty, so it has at least one element, possibly even more, we don't know. But whatever element that AI intersection AJ has, this X, so X is already occurring in AI and AJ, which means that X cannot occur in any other third set AK. So now what are this A1, A2, AN sets that we have, right? So let's make pairs of such sets. So A1 and A2, A1 and A3. So like that, if we make pairs of every two sets, AN minus 1 and AN. So how many such pairs will we get on the left hand side?
N choose 2.
N choose 2, correct. So we have N choose 2 pairs available here. And what every such intersection will have some element inside that. And what we are observing is that, let's say the first element is X1, second element is X2, and last element is some whatever Xn2. Okay, so you see there is a one-to-one correspondence between every pair here and the corresponding element X1. Okay, because as we already said, that X1, once you have committed that X1 belongs to A1 intersection X2, X1 will not occur anywhere again in this list. So what that means is that this number of elements X1, X2 and Xn choose 2 has to be equal to this the pairing that we are showing on the left hand side. And now do you see what happens? Let's say n is greater 6 or n is any number greater than 5. Then n choose 2 will be more than 10, right? But we don't have 10 distinct elements to assign over here. Our set S considers exactly 10 elements. So no matter how clever you are, there is no way to put one element in each row over here. Okay, so that is the logic which ensures that, I mean, no matter how clever somebody is, there is no way of assigning 6 sets with this condition. Okay, so I hope everybody follows this approach. So that tells us that it can be, answer can be at most 5, but can 5 be achieved or not? So for that, I think the trial and error approach, which I think many of you have already tried, that will work. So I think to trial and error, you will realize that now that in fact this information gives us something very important, that every pair of elements like A1 and A2 intersection will have some one element. So let's start assigning that way. So let the common element of A1 and A2 be 1, then A1 and A3 be 2, etc. So we can just make the ticks that way, so that in every case we are taking a different combination of 2 sets at a time. Okay, so this is a valid construction which satisfies all the conditions, and that is also the maximum possible answer. Okay, so I mean, I know that I asked this problem like IOQM style, where the only final answer was supposed to be written, and I think many of us will get away with just, we'll do this trial and error, we'll get the answer as 5 and we'll write it and move on, and you'll also get the marks for that. But we should not stop now that we have time available. We should not stop at just getting the answer, but we also need to look at the logical explanation. So some reasoning like this is required to be sure that the answer cannot be greater than 5. Just your intuition is not enough. Okay, Raghav, did you have something similar or a different approach?
Yes, almost similar. I just counted the number of elements, like sum of all AI, number of elements in AI to be 20.
Okay.
And then I said that, like, we look at AI and all the other sets, there has to be only one element in common.
Right.
You get, say, n, so you get n minus 1 elements. So n times n minus 1 should be 20. So you get n equal to 5.
Oh, okay. Interesting. Can you repeat your idea? I think that sounds interesting. So,
Yes.
first thing I think what you said is that if we take the sum of the elements, as you already said that each element in S can occur in at most two such distinct subsets. So if you just take the sum of the values on in all the set, this will be less than equal to 20, right?
Yes, sir.
Okay. After that, what do we do?
And now if you say if you look at set A1,
Okay.
and then between A1 and A2 there has to be one element in common.
Yes.
A1 and A3 there has to be one element in common.
Right.
So in total, like from A1 to AN, you have n minus 1 such elements.
Yes, correct. So A1 intersection A2, A1 intersection A3 up to A1 intersection AN. This will have n minus 1 elements.
Yes,
Correct.
which gives us that A1 has to have at least n minus 1 elements.
Yes, okay, correct. So A1 has to have at least n minus 1 elements. Correct.
So this will be for all AI. So total number of elements would be n times n minus 1 bare minimum.
Okay, interesting.
And then you get that, then if you equate both of them, you get n equal to 5.
Yeah. Got it. Yeah, this is a very nice approach. So I hope everybody followed what Raghav is explaining, that first we get this condition based on basically how many ticks are there in this whole table. That is what we're counting here, right? Sigma AI is the size of the first subset. So the number of ticks in the first row, second row, etc. So that total will be less than equal to 20 because every individual element can be in at most two sets. And then looking at A1 as an example, so A1 intersection A2 up to AN, this is going to give n minus 1 elements and importantly distinct elements, as we also observed. So if they are all distinct elements, it means that the size of A1 has to be at least or equal to n minus 1. And the same will be true for every single set. A2 will also be at least n minus 1 all the way up to AN. So if we add all of these together, basically what we are getting is that this exact same sum has to be greater than n times n minus 1. And that puts a natural condition on n. So if n times n minus 1 is less than or equal to 20, then n has to be less than 5. Okay. So actually, both approaches are useful in demonstrating something like a good problem solving technique. This approach which Raghav explained, right? I would like to call it some kind of accounting approach, that you have to account for how many ticks are there in the grid. First, we account for them one column at a time, and the same thing can be counted one row at a time. So you see that basically LHS is counting them row wise and RHS is counting them column wise. So that is how we are accounting for the same information. Okay, I think anyway we have spent enough time on this. So for every week I will mostly having the same pattern, 3 questions kind of easy and 3 slightly harder questions at the INMO level. I would encourage you to look at all of these questions for now as if they are all subject to like norm form questions. So even if the answer is like find the largest possible value of n, the expectation is not that you just find a numerical answer, but you also try to find this explanation. Because even if you are not going to write the explanation in next year's IOQM paper, that logical development will be useful one way or the other. Okay. So with that, I think let's move on to the other 3 problems for today. So question 4, 5, and 6. So these are slightly harder versions, in some cases quite hard, but basically the difference between the first half and second half of my lecture is not going to be that some very advanced theory is going to be done. Finally, Olympiad problems are just that how many like middle steps are there, how many intermediate steps are there. So just these questions will have slightly larger number of intermediate steps, but ultimately these can also be solved by everybody. So I'll leave it for you as students to take a call which half you want to attend. Most important thing is optimizing your own time. Okay, if you are going to spend whatever hours attending my lecture, you should get the maximum benefit out of that. So keep that in mind. If somebody who is already advanced, they see the first 3 problems as very easy, then don't waste your time on that. You can attend just the second half, and vice versa. If somebody is still struggling with the basic ideas, then there is no point in trying something harder. That might only waste your time. So take your call accordingly. Okay. Okay, so with that, let's jump to questions 4, 5, and 6. Again, I'll give you some time to think, maybe 15, 20 minutes
I
at least.
think question 6 is quite similar to what we did right now.
Question 6 is quite, in fact, I'm going to bring that similarity out for everybody. But so is the answer of this 10?
Yes, sir, I got 10.
Okay, but are you able to prove that it cannot be smaller than 10?
Yes, sir.
Okay, fine. Okay, we will look at that then. But yeah, we'll start from question 4.
Sir, what do you mean by homogeneous polynomial?
Homogeneous means all the terms have the same degree. So you cannot have a square and we actually. So homogeneous in one variable, if I have a homogeneous polynomial, not in one variable doesn't make sense, but in two variables, then basically if one term is of the power of 10, then all terms have to be of the power of 10 only.
Okay, sir.
You cannot have a term like x square y in the mix. So
Okay,
that's
sir.
all.
Thank you.
And that Pn of ABC means that homogeneous equation should be of degree n.
No, it need not be of degree n. Just a notation that the polynomial corresponding to small n is denoted by Pn.
Okay, sir. Sir, I have a doubt about definition of homogeneous polynomial.
Yeah, tell me.
There is the constant polynomial or zero polynomial, homogeneous polynomial.
Constant polynomial can be considered homogeneous, but not zero polynomial. Because zero polynomial cannot be assigned any degree.
Okay, yes, sir.
Yeah, even I was thinking about that when I wrote the question, that whether I should have a condition that says there exists a non-trivial homogeneous polynomial just to eliminate the zero case, but ultimately I decided not to do that. So we already have P1, and because of what we saw in question 1, we also know P2 now. What can be one possible? And by the way, note that I'm not claiming uniqueness. There could be more than one such polynomial, but as long as you can find one polynomial, that is sufficient. So how can we write P2 as?
A square minus B square minus BC.
Yeah, correct. So we already know that a square root of b into b plus c is the condition. So just rewriting that as a square minus b square minus b c equal to 0. So P2 of ABC. And in this case, it turns out to be an if and only statement, that if there is a triangle whose sides satisfy this relation, that this is equal to 0, then it will be a equal to twice b, and vice versa. I think in general also that polynomial will be if and only if, but I am not given to claim that for sure. So that's why I am only given one direction here, that if a equal to n times angle b, then the polynomial will be equal to 0. But that will be an open exercise for you to see if the reverse will also be always true or not. So just to get started, let's see if we can find P3. Suppose we have a triangle where one angle is 3 times the other angle. Then can we figure out some way to solve that? That will be the first step, right? If we can do P3, then there is hopefully we can continue the process further. Because directly reaching a equal to nb n times b seems there is a solution for that also, where you can directly claim the n level answer. But let's start with some small steps. So let's do one level at a time, P1, P2, P3.
I think we can, by induction, we can do for the nth variable.
Right, very
Like
interesting.
we don't get the polynomial, but we
Huh.
can prove that there exists a polynomial.
Right. We don't have to write the polynomial explicitly. We just show that it has to exist. And if you already solved that question, can you think of how to extend it for n, which is not just a natural number, but also a rational number, positive rational, such as some p upon q?
Okay, sir.
Okay, so let's see how we can approach P3. That suppose one angle is 3 times the other angle, what can we do? Okay, so the diagram is x and 3x, and we have to find some relation between the sides of the triangle. So same as before, earlier we had taken the angle bisector, right? Because the angle A was 2x, so we could take the angle bisector. Here, taking the angle bisector of A will not be that useful. But which other line can you suggest we should draw to give us something useful? And as Arna has already mentioned that we want to think of this like induction. So we already have the P2 result available. So if we have any triangle where one angle is twice the other angle, we already know what to do with that. So we just have to create that scenario in this diagram. So what should be the construction to do that?
2:1 ratio.
2:1 ratio, right?
Angle BAT should be 2x.
So that is the solution which I know, but now I'm just taking a pause and thinking, is the other solution? No, but there you will not get x and 2x in one triangle. Okay. So if you split this angle as x and 2x, let me just draw the other diagram for 1 minute. What will happen if I draw it like this? X. I'll get an isosceles triangle, but in this case, luckily, this will also. So in fact, I'm getting two isosceles triangles like that. Maybe something can be done for this particular approach. Like here, luckily, I'm getting two isosceles triangles. But in general, if you want to go to the nth term, then the left diagram is the right. So here, once we draw this AD, you'll see that we have two triangles and both of them have something useful for us to give. So triangle ABD satisfies the previous condition of P2, right? One angle is twice the other. So we'll write the equation of P2 for triangle ABD. And what about triangle ACD?
It is similar to the original triangle.
It is similar to the original triangle because once again you have the same pattern. So you see this pattern will keep recurring in so many places that your mind should get trained to spot it quickly. So this angle X and angle X here, like alternating equal angles and this C being the common angle. This pattern occurring frequently, something that should become a part of your natural instinct. So therefore triangle ACD will be similar to triangle BCD. And quite similar to how we had written the ratios earlier, we can write something here also. And notice that in triangle ABD, when I apply the P2, because triangle ABD satisfies the condition that angle BAD is twice angle ABD, right? So when I'm applying P2, the coefficients of P2 are, or this Pn in general, are carefully arranged. They are not arbitrary. So Pn in general, the three values in that equation of Pn are such that the angle opposite the first term A is n times the angle opposite the second term. So that is the order which has to be followed all the time. So keep that in mind. So therefore, when I'm applying P2 for this triangle ABD, I have to write P2. What should be the first term in my equation? It should be the side opposite the larger angle. So BAD is the angle here. So BD should come here. Okay. the second term should be the angle opposite, the side opposite ABD. So AD, and the third side should go here. Okay. So P2 allows us to state this fact that because the angle is given, P2 of this product is 0. So we have this information and this similarity. So can you put both of these things together and try to come up with a possible definition for P3? And we want P3 in terms of the original ABC finally. We want the original ABC to be involved. In this, only this term AB is equal to small c. But BD and AD are, we don't have any expression in terms of ABC here. So that is the only thing left, right? If you can convert BD and AD into some expressions involving the sides of your original triangle, then we are done. Okay. So from the triangles given on the left side, we can write these ratios, right? AC upon BC equal to AD upon AB to CD upon CD. In other words, B upon A is equal to AD upon C is equal to CD upon B. So that gives us the way to find AD and CD. And once we have AD and CD, we can find BD also, right? So AD is B into C upon A, and CD is B square by A. So if CD is B square by A, how much is BD? BD will be A minus B square by, so BD will be A square minus B square whole thing upon A. So we can substitute these values now, AD and BD in this equation. So we can write P2 of A square minus B square upon A and B into C upon A. So now the interesting thing to realize is that this itself, we don't know if it's a polynomial yet because we have A in the denominator, but we can, what we do is, so we know that P2 is a homogeneous polynomial, right? In this case, we know the exact expression of P2 also, but we don't need to look at that. If we just multiply the whole polynomial with A, right? Basically, I can take this A from the denominator into the numerator. So I'll be left with A square minus B square, BC and AC. So when you take a homogeneous polynomial like P2 of x, y, z, where homogeneity what it guarantees is that every term, if let's say the degree of this polynomial is some k, so then every term is of the form x raised to I, y raised to j, z raised to k. Let the degree of this be t. Then what is guaranteed is that it is comprised of sums of these kind of terms where I plus j plus k will be t all the time. And in this polynomial now we are substituting these values a square minus b square, bc and ac, which are themselves homogeneous of degree 2, right? Each of these is of degree 2. So what will be the, when I substitute this, the new big polynomial which I get in terms of ABC, what will the degree of that polynomial be? If this, the polynomial of the P2 is of degree t, do you see this polynomial will be of degree basically 2t?
Yes, sir.
Because wherever x was occurring, x will be replaced by a square minus b square. So the degree is increased, like basically getting doubled. Okay. So anyway, this was not asked. We don't want to find the degree, but it's good to check that. So in a way, basically you see that polynomial P1 was of degree 1. That is just simply a minus b. P2 was of degree 2. P3 will be of degree 4. So in general, the nth polynomial will be of degree 2 raised to n minus 1. And I should say at most, because as it turns out, sometimes factors get cancelled out. For example, if you actually find the polynomial of P3, let's do that. Find actually what is P3 ABC by doing this substitution. So what the substitution we want to do is, so P2 in terms of x, y, z is x square minus y times y plus. So if I substitute that, the P3 I'll get is a square minus b square whole square minus bc times bc. So this is my P3. So right now it is looking like a degree 4 polynomial, homogeneous degree 4 in ABC. But you'll see that there is a copy of a plus b which is common to everything, right? So if I take a plus b common, I'll get a plus b times a minus b whole square minus b square. Okay, do you see this? That this is the polynomial, and it is safe to cancel a plus b because we know that we are dealing with only positive sides. So a plus b will never be 0. So it is we can define P3 as this polynomial also. P3 ABC as just this part. In that case, the degree of P3 is no longer 4; it is 3. But I mean, in general, when such cancellation will happen and will not happen is very hard to say. But I mean, for us as humans, it is very hard to keep finding the next term this way, P2, P3, P4. But a computer can quickly do this substitution and get the next term. Okay. So important in this proof, if you realize that we never use the fact that this angle was 2x of x. I mean, this 2x could be replaced with n times x, and the same argument would hold true also. So I'll encourage you to try this out, that repeat this whole calculation, but now do the induction step. So suppose now we have Pn available to us. Okay, we have the Pn polynomial, and we want to find what is Pn plus 1. So to find Pn plus 1, we consider a triangle ABC, where angle A is given to be n plus 1 times angle B. So if this angle is x, this angle is n plus 1 times x. And you'll do the same construction as before. You'll draw that line, you'll split the triangles and everything. So I mean, the rest of the calculation remain exactly identical, and you'll end up with this conclusion that basically the next level expression Pn plus 1 of ABC can be written in terms of Pn with this exact same substitution that we did here. A square minus B square, BC and AC. Okay. So this is the kind of recurrence relation you can say, which allows us to compute the Pn for any arbitrarily large value of n. Okay, so I hope this is clear, and realize that we are using very simple tricks to do this. What did we use really? Only similarity, right? Everything is coming from just similar triangles. So just repeated application of similarity is able to give us really big returns over here. Okay. There is one more approach which I have in mind, but before that, anybody wants to ask anything or any other approaches you may have?
Sir, I tried this using algebra.
Okay.
Like I tried to represent, like I was able to prove that we can represent cos of n times x in terms of cos x.
Right.
And like using induction, we can prove that, and then we can replace everything in terms of ABC.
Yeah, correct. Yeah, that is perfectly valid. That in fact that was the idea I was thinking about also. So cos of, I mean, this requires some trigonometry to be, I mean, just familiarity with trigonometry is sufficient. But for example, we know cos of 2x is 2 times cos square x minus 1. Cos of 3x, I always forget cos of 3x for some reason, but I can find it cos of x plus 2x is cos x cos 2x minus sin x into sin 2x. I don't know why I always forget cos and sin 3x formula. But anyway, so here sin square x will become 1 minus cos square x. Okay. So you see again cos 3x can be written in terms of purely cos x. Okay. So we'll get 2 cos cube x minus cos x minus 2 cos cube. Just 2 cos cube x. So finally you'll get 4 cos cube x minus 3 cos x. I hope my answer is correct. Anyway, the point is that cos of nx in the same way, right? By induction, you can show that cos of n times x can be written as a polynomial in terms of cos x. Okay, so, but it's not going to be homogeneous because here every term will have a different degree. But doesn't matter. You'll get a polynomial anyway. So you get some sigma, some coefficients ai cos of x raised to I, where I goes from 0 to n. Okay. And in fact, some of the terms will be missing and all of those things. But so cos of nx can be written in this way. And then, so after that, what do we do? I don't know.
So then I was thinking like somehow we can manage the degree, but I'm not sure how.
So let's say we have ABC here, and I mean the idea I assume is that you want to use cosine rule here. So we'll get cos of nx can also be written as
B square plus C square minus A square by 2BC.
by 2BC is equal to this whole expression, and here we are getting cos x. Now cos x itself again has to be written in the same way. So cos x will have to be written as, yeah, it looks very complicated because cos x in our diagram opposite angle B. So C square plus A square minus B square upon twice. I mean, this entire expression on the RHS which we are going to get sigma AI cos x whole raised to I. There this thing will get substituted, whole thing raised to I. But I don't think we should be worried now, because see, if you notice right now, this is both sides are 0 degree polynomials, right?
Yes, sir.
So the degree will remain homogeneous. There should not be any worry about
No,
that.
sir. What I was thinking, like if we have no, sir.
And
Yes,
what could go wrong?
it will
should work.
remain homogeneous.
And we have to clear out the denominator. So we have 2BC over here, and the RHS will have in fact AC whole raised to I. So to clear the denominators, we have to multiply everything by
You can multiply it
AC
by AC raised to n because that's the
n and n to d or something. So, but it will work out. So I think this is a fine approach. Of course, this relies on this assumption, or rather something we need to prove as a lemma first, that cos of nx can be written as a polynomial in terms of cos x. Actually, this is a kind of a well-known result. So even if you are short of time and quickly mention this, you can probably get away with that. So you don't have to prove it also, because as you say, it's very trivial. It's like 2x, 3x, the same pattern continues. So that is one approach to do this problem. Okay, then I have asked the question to Arnav, and maybe others can also think about this, that here we are dealing with a equal to nb, where n is an integer, positive integer. What if we consider a as n as a rational number, positive rational? So what if we are considering I don't know what is the year today, 2022. 2022 times a equal to 2023 times b. Sounds very crazy, but there exists a polynomial which will be satisfied by only the triangles where this condition is true. So that is something for all of us to think. And this is where surprisingly some number theory is very helpful. Because what is the connection between rational numbers and natural numbers? That is what this is all about. In fact, in Burton, there is a whole top chapter dedicated to this. This is beyond what we have done. We only went up to the like Fermat's theorem, Euler's theorem. But as I explained earlier, also I encourage you to look at the other chapters, because there are really a lot of beautiful mathematical properties there. And particularly the chapter of continued fractions is where you'll see a lot of useful ideas.
Then in this also won't the same proof work? Like we can represent cos of like let the common factor be x, so we can represent cos of 22 point times a in terms of x and cos of 2023 times b in terms of x.
Yes, that will work. That will
And
work,
then we
but
use that x 2022 times a is equal to x to get the relation which from the first thing which we did right now.
wait, but don't you think there will be a problem there, because you will get a expression in terms of x, but what about, I'm not clear about how we are going to, because finally a and b themselves, you know how to write the cos of a and cos of b. Let me see what if I understand what you're saying. So cos of 2022 a is equal to cos of 2023 b, and now this can be expanded as a polynomial in terms of cos a. So sigma some ai cos a raised to I, and this will be sigma cos of some bi. Oh, sorry, bi cos a. And then here cos A and cos B themselves can be replaced by the cosine rule expressions. And therefore we will get a polynomial in the end. That is correct. That is true. That is definitely possible, but let's see if we can do this without trigonometry. What about the approach we were doing earlier, like P2, P3, P4? Can that approach be somehow used to find the answer to this question?
So actually, like I was trying an idea to solve the problem,
Sure.
but it did not work out. What I observed was that like if you take the like line, if you take D on BC, such that angle CAD is X, then you can observe that like in the original figure. So is
Okay.
for example, in this one, in this triangle, you can see that the circumcircle of ABD would be and AC would be tangent to the circumcircle of ABD.
Yes, correct.
I tried to use that, but I could not go like go further.
Yeah, actually, in a way, we are using that property when we write the similarity, right? Don't you see that the first and third term is basically CA square equal to BC into CD? That is referring to the power of the point C with respect to that circle, right?
Yes.
Yeah, but I think apart, I mean, through that also you'll realize you'll come back to the same calculations. I don't think there will be anything more from there. Because ultimately the reason why this approach works is because of this remaining angle, right? 2x and x. That is, or in general, n times x and x. So that is the induction causing step.
Okay.
Yes, but what about rational numbers?
Well, if we're trying to prove for rational number using normal geometry, then I think we'll have to do a two-step induction, like induct on n and then induct on m.
Okay, so if your rational number is some p upon q, then you want to first induct connect this to p minus 1 upon q and then p upon q minus 1, something like this.
Yeah, like we show that for some like if we start from p to then q, then
Okay.
we show that for some q all the p work, then for q plus 1 all the p work, and then we show that for p for some p this is satisfied by all q, then for p plus 1 that is satisfied by all q.
Right. Yeah, that is one idea definitely. Actually, you will find this hard to work out because if you see the connection between p by q and p minus 1 by q, right? Just try drawing the diagram. I mean, the key idea which helped us was that when that remainder angle, right, that x was equal to the base angle, that gives the additional similar triangle. In if you try to do this kind of induction, right, whatever line you draw, I mean, you'll one angle will be such that you can apply the induction hypothesis, but the remaining angle, if it is bad, right, now the remaining angle will be 1 by qx, and this is x. So there is nothing much you can do now. So your idea is correct, but just think about what is the induction step. I mean, what is the jump you are going to make here?
Then maybe we can take p minus q by q.
Exactly, correct. What if you take p minus q by q? So that let's say assume that p greater than q is we are starting with. So then that will work. That is exactly right. P minus q by q will work. And we have to keep doing this jump basically of q steps at a time until we reach a point where the numerator becomes smaller than the denominator. At some point we'll reach a fraction like maybe 2 by 5. Now the numerator is smaller than the denominator, so we cannot continue this process now. Okay. So actually, the idea which Arnav is saying is on the right track, but I think there is a slightly better way to represent it, which will be easier for all of us to follow also. Let me ask a very simple question. We have P2, right? We know the definition of P2, whatever it is, and that is satisfied by all triangles where A is equal to 2B. Do we have P half? P half is the condition which is satisfied if A is equal to half B.
That's p2
Yes.
of BAC.
Exactly, right? I'm just going to exchange the position of A and B and I'll get P half. So P half is nothing but P2 of BAC. Everybody agrees with that? And in general, for any natural number n, what is Pn of ABC going to be? Same logic, right?
BAC.
Pn of
of
BC.
BAC. Because if A is equal to n times B, then B is 1 by n of A, right? That's all we are going to be looking at. So we already have this polynomials for all the reciprocals of natural numbers.
So sir, if we prove for denominator less than numerator or denominator greater than numerator, then we are done.
No, sorry, can you repeat that?
Like if we prove that for p less than q, that thing is satisfied, then we can say that we are done, because for p greater than q, we can just write it as q by p times that. So
Yeah, I mean, coming back to your induction approach, right? So if you start with P upon Q where P greater than Q, you can keep subtracting and you get, but once you reach a point like this where numerator is smaller than the denominator, then what do we do?
No, sir, I'm saying that if we prove for any one of like independently, if we prove for P greater than Q,
Okay, yeah,
then it
correct.
satisfies that for P less than Q also that thing works.
Yeah, correct. That will be, but that will be harder, right? I mean, P greater than Q, you are making the question harder for you.
Like P less than Q, you mean we start with?
No, I mean, in the sense that if you're, let's say your starting polynomial was 17 by 5, and you are able to repeatedly subtract and obtain 2 by 5. So what you're saying is correct. If we find the answer for 17 by 5, then it will be true for 2 by 5 also, and vice versa. But out of the two, obviously 2 by 5 is the easier to attempt, right?
Okay, so we start with P less than Q.
Huh.
Independently, we try to prove for P less than Q.
If we can do that, then we are done. But now do you see what I mean? You are almost there. Just one final step missing. How we are able to obtain all of these expressions? Whatever is your, let's say, whatever is your final polynomial or final rational number P upon Q, where let's say P is less than Q, and unfortunately the same capital P small p, but anyway, that's so I am interested in finding this polynomial capital P upon Q. What will that be equal to? I know how to deal with the numerator greater than denominator.
P of Q by P times BS.
Exactly. So I just flip the numerator denominator, and once again I can continue the process. Okay, so I think we have been talking too fast. I don't know if everybody is with us, but so let me just illustrate this with an example. Let's say I want to find polynomial of 17 by 5. Okay, I want to find this polynomial which is satisfied only if a is equal to 17 by 5 times b. As crazy as that sounds, such a polynomial does exist. So the approach we are thinking is like this. What we did in the first half, right? Basically, we have the induction step to go from Pn to Pn plus 1. So we know how to add 1. And now what I showed that we know how to do the reciprocal. So if I have some PR, I know how to find P1 over R by just exchanging the A and B, right? So we have these two operations available, adding 1 and taking the reciprocal. And if we apply this repeatedly, you can reach from any point to any other point. So 17 upon 5 can be written as 1 plus 1 plus 1 plus 2 upon 5, which can be written as, and why am I writing 1 plus? I just write it as 3 plus 2 upon 5, which can be written as 3 plus reciprocal upon 5 by 2. And now once the 5 by 2 numerator is greater than denominator, I can again split it as this will be 2 plus half. So 17 upon 5 can be written in this form. And if we have this information, now what do we do? We start with the lowest point. So we know P2. Okay. So P2 is known. Then P half will be just P2 with BAC reversed. So we know P half. Once we know P half, we have to add a plus 1 2 times. So we can get P5 by 2 by just adding that induction step 2 times. I'm not writing it here. So I'll get P5 by 2. Now I want P2 by 5. P2 by 5 will be just P5 by 2 and B and A interchange. So I'll get 2 by 5. And finally, once I have 2 by 5, I just have to add 3 times. 3 to that. Basically, I have to add 1 3 times, and that will give me 17 by 5. So in principle, all the steps can be done. The calculations are beyond our capacity to do on paper. Okay, but the fact that every rational number can be expanded in this way is exactly what we call finite continued fraction. Okay? So if you're interested in this topic, just look at Burton's, I think last or second last chapter. They deal with finite as well as infinite continued fraction, and that is what allows us to do this problem. Okay, but anyway, we have spent a lot of time on just one question. But you see how, I mean, you can take one starting point and explore it in so many different ways. So it's important for us to do that for every question that we solve. Okay, that was question 4. Now let's come to question 5. Arnav, you already have a solution?
Yes, sir.
Okay, let's wait for everybody to try. So for others who are still trying the question, first thing is start doing some small experiments, take a few values and observe some patterns.
So I think I've got an idea, but it's not almost. I got the formula.
Okay, formula in terms of the prime factorization or in some other how?
Uh, in like phi of n.
Okay, okay. But I mean, yeah, I think I get an idea of what formula you're referring to, but is that able to prove the multiplicative property?
We know
From
that
that?
phi is multiplicative, but the
Yes.
problem is there's like phi of x upon x is that kind. So I don't know if that
Hmm.
will work.
Correct.
Actually, I got the same formula and it works. I think it works.
Hmm. Actually, there is a in chapter 6 on Burton, there are a few useful properties. If you know that a particular function is multiplicative, you can use that to construct other multiplicative functions. So that kind of approach should work out. But I'm also not sure of the details. My proof is completely different. I don't require the phi function at all. So I'll have to look at your proof. So Arnav, you are able to complete using that Euler function.
Yes, sir.
Okay.
They prove that it's multiplicative. Got it.
Yeah, correct. Okay, so just as a hint for others to indicate the idea which Arnav and Raghav are mentioning. If you look at how the psi of n is defined, psi of n is the sum of the GCD of I and n, where I goes from 1 to n. Now, clearly the GCD of n and any number has to be a divisor of n, right? So this I of n, this term, the GCD, we are only going to take one of a few finitely many values. So if you consider all the divisors of n, right? Let's say the divisors of n, the list is d1, d2 up to some dk. Okay, so these are the divisors of n. So for every value of I, the GCD is going to be one of such terms. And if we look at how many in general, let's say dj, okay, so the divisor dj, we want to see how many values of I are there such that the GCD of I and n is dj. Okay, so I and n GCD is dj. Suppose this is what we are looking at. Now you will see that this is equivalent to the condition that if I divide everything by dj, so I upon dj is equal to 1. The two are completely equivalent. And not only that, in terms of range also. So I in our original summation is going from 1 to n, right? Or I greater than 0 and I less than equal to n. So when I divide by dj, I get I upon dj is also between 0 and n upon dj. So in this part, if you see that everywhere we are getting n upon dj, can be replaced if you are not comfortable with the notation with some other symbol, but basically what this is counting is the number of terms between less than or equal to n upon dj, which are co-prime to that. So in other words, this is counting nothing but phi of n upon d, right? So in other words, in the column of dj, exactly these many terms will occur. So therefore, this summation can also be written as not in terms of I going from 1 to n, but in terms of all divisors of n. So for every such divisor, there will be phi of n over d terms, and each term will contribute d to the summation. So summation of d times phi of n over d, where d goes to all the divisors of n. So this is one more formula for psi of n which you can write. And then using this, we can show the multiplicative nature of psi of n by exploiting the fact that phi is itself multiplicative, which we already know. Okay, so is the at least the first part clear, that how we are obtaining this expression itself by counting in terms of the term itself. So the I comma n, what are the values it can take? That is what we are doing. And see, again, once more we are doing something similar to the proof which Raghav gave, right, for the A1, A2 set. We're kind of accounting the same thing in a different way. Here also we are doing the same thing, right? If I take a numerical example, let's say n equal to 6. Okay. So if you look at numbers 1, 2, 3, 4, 5, 6. And here I'll list the divisors 1, 2, 3, and 6. So these are the values of the divisors themselves, and these are the values of I. So I mean, here basically when I is 1, the GCD is 1. When I is 2, the GCD is 2. When I is 4, the GCD is 2. When I is 5, the GCD is 2. So the way our original psi of n is defined, we are adding this row at a time, because we are saying what is the first value, it is 1, 2, 3, etc. We are just now combining it in terms of, sorry, we were initially adding it column at a time, but now we are going to look at it row at a time. So we take the first row and look like 1 times how many elements are there in this first row. So 1 times 2. So 2 because phi of 6 upon 1. Okay, yeah, 5 of 6 is 2. So I don't know why I got confused there. Then the second row has 2 times phi of 6 upon 2, and that way. So we are counting the same object in 2 different ways. So I hope that analogy is clear, that how we are doing the same thing. Okay, so once we get this expression, and now to show the multiplicative part. So if we write out the expression of psi of m and psi of n in exactly the same way, but what we'll do is, because we want to multiply them together, we can use different subscripts. So let me call d1 as the first variable.
Sir, actually, it would be better if you simplify that first equation or first expression for n first.
Yes, sir. You can write n by d as d and
Yes,
d by
like
as n by d.
as the summation covers all the divisors of n, we can just replace that there n d by n by d and n by d by d. That expression is easier to work with.
Okay, no problem. Yeah, that is fine. It will be equivalent, right? But I mean, I don't think there is any difference. I mean,
Because
maybe
there we can take the n outside and work with that.
Yes,
okay.
that's what I did too.
Okay, let me see what you're saying, because I think it will be equivalent to, that doesn't really matter. So can you repeat what you're saying? Basically, we are going to replace n by d and d by n by d, right?
Yes, sir.
Okay, so this is sigma. So the summation range remains same, but now we have n by d times pi of d this way. So therefore, yeah, we can pull out one value of n, that is so sigma 1 by d into pi of. Okay, so this is psi of n, and now psi of m will be m times sigma d divides m 1 over d psi of pi. Okay. So now here, as I said, just for convenience, let's use different subscripts. So let this be d1 and let this be d2. So that when we multiply them together, So multiplying psi of m and n together, psi of m times psi of n. So we are basically multiplying two sigmas. And yes, okay, so that therefore to get mn out common, we are saying that. So that d1 divides n sigma d2. Okay, so this is actually two summations being added that way. So what will happen when we expand the brackets term by term? Every term from the first bracket will get multiplied with every term from the second bracket. So in all, the whole thing will look like mn times basically it will be a summation of d1 divides n, d2 divides m. So every possible index from the left hand side and every possible index from the right hand side will combine, and the terms that just will also get multiplied. So we'll get d1 d2 phi of d1 phi of d2. So this is what that summation is looking like. Okay, and now do you see that from here we can quickly jump to because we know that d1 divides n, d2 divides m, and n are given to be co-prime. So therefore I can combine d1 d2 into a single term d, right, which is the product of d1 d2. And basically whatever indices are traversed by d1 and d2 separately, they will also be traversed by d divides mn. So there will be one-to-one correspondence between both of these terms, and therefore we can write. And in the same way, now the phi of d1 and phi of d2 can be combined into phi of d1 d2, which is simply phi of d. Again, because d1 and d2 themselves are co-prime, and you have mn over here, and so we are left with psi of m. Therefore, psi of m into psi of n is equal to psi of m. Okay, so yeah, this is one approach to solve this problem. In a way, it involves a lot more algebraic manipulation than might be required for this problem, but it's instructive. Actually, it's a very systematic approach because we are converting something unknown, something psi of m which we don't know about, into something which is familiar, such as phi of d. And this combination of pattern is very typical, like two sigmas coming together and the indices getting combined this way is something that you will see often. Okay, so then what is another approach to look at this problem? So here is one possible idea. Let us look at psi of mn, this sigma of 1 over mn plus 2 over mn plus, in general, let's say some I over mn, some random term, and last term is mn comma n. Okay, so this term the GCD of I and mn, and I want to finally reach psi of m and psi of n, where we are taking GCD with m and n. What can you say? Can you see how to write this in terms of GCD with m and n separately? Yeah, you can take a few numerical examples to check if you want. Let's say m is 6 and n is, I don't know, 7, let's say, doesn't matter. And I is some, let's say 21. Okay, so I comma mn, this is GCD of 21 and 42. This is 21. A kind of boring example, but can you see some other way to compute the same answer?
GCD of 6 comma 21 into GCD of 7 comma 21.
Yes, correct. So my claim is that GCD of I and mn is GCD of I and m into GCD of I and n. And this only happens because mn are co-prime. Okay, I will give I'll give a couple of minutes to see how to prove this. Simplest way, whenever you have this kind of thing, is periodic valuation. Periodic valuation solves everything. So take any prime P and let I, M and N. So let the VP of I be alpha, VP of M be beta, VP of N be gamma. And you can just write LHS and RHS in
And
terms
at
of
least one of alpha, exactly one of beta and gamma is 0.
exactly one of beta and gamma is zero.
No, actually, at least.
Not exactly. It
At
can be
least.
because P can be any bracket. So at least one of P, beta gamma is 0. Beta is 0 or gamma is 0 is given. And now if you see the LHS and RHS, what will be the periodic valuation of both sides? So LHS, what will the periodic valuation of the LHS? So GCD means you take the minima of the indices. Right? So this is the minimum of alpha and beta plus gamma. This is the LHS, and the RHS is minimum of alpha comma beta plus minimum of alpha comma gamma. So will this be equal?
Yes, you can say without loss of generality.
Yeah. So let's say without loss of generality, gamma equal to 0. So if gamma is 0, then this is simply alpha comma beta, minimum of alpha comma beta. And on the right hand side, I mean, because we are all of these are greater than equal to 0, I mean, this will be nothing but 0. So this will be directly equal to 0. Okay, so therefore I comma mn is im into in. So therefore our sigma or original psi of mn can be written as sigma I going from 1 to mn GCD of I and n into GCD of I and n. And now do you see how to complete the proof? Why will this be equal to psi of m into psi of n? I mean, psi of m is nothing but 1 comma m plus 2 comma m all the way to m comma m. Right? This is psi of m, and this is being multiplied with 1 comma n plus 2 comma n plus n comma n. So when I multiply the RHS, I'm going to get a lot of like cross products, and exactly mn products will emerge from the RHS. And do you see a reason why there will be a one-to-one correspondence between the RHS and the LHS now? Of course, I itself is going all the way from 1 to mn. So in the RHS, these 1 to m are finite. So this is only going up to m, and this is only going up to n. So how about this? See, I can be written as some, if I divide it by m, right? Basically, I can just look at the remainder where r is less than m. So if r is the remainder of when I divide I by m, so what will I and GCD of I and m is nothing but the same as GCD of r and m, right? And r comma m is going to lie in this list. Similarly, when I divide I by n, I'll get some q2, let's say q2 n plus r2. So then the GCD of I and n is nothing but the same as GCD of r2 and r2 and n is going to lie in this list. And something which we already done when we did the multiplicative nature of phi of m, that these r1 and r2 pairs are going to be exactly one pair is going to come for every value of I, right? As I traverses the range from 1 to mn, these r1 r2 pairs are going to, all of them are going to occur in exactly once each. So therefore there will be like a one-to-one correspondence between every such im into in and the corresponding remainders in the RHS. Okay, is everybody able to follow this?
Yes, sir.
Okay, Raghav, you want to add something or your hand is up?
Sorry, sir, I forgot to do.
Okay, no problem. Okay, so this is one more approach which you can add. And I'll have to think if there is one more, even third approach could be possible, but right now I'm not able to think of that. So, okay, so then coming to question 6. So as Arnav was mentioning earlier, right, question 6 and question 3 look so similar that there has to be some connection. And that
Just a
is
small
that is-
adjustment works, like
Yeah.
transformation.
Correct. So just the complementation of the first question becomes the second question, right? But I was able to observe that, but I don't, at myself, I don't have a proof of that yet, that why 10 is the smallest possible value. So if I have less than 10, if I have 9 elements, do I get a contradiction? Is what you are able to show?
Yes, sir. Actually, I showed that the minimum possible value is 10 without contradiction.
Oh, okay. That is useful then. But anyway, before we look into the question, right, I want to motivate this like a puzzle, and there is a real value application to this question, which I don't know if anybody has thought about, but this is the problem actually. There are 5 scientists, okay, and the 5 scientists are working on a top secret project in their lab, and every day they come in the morning, they open their there is a safe, and that safe contains all the material, all the confidential material related to that project. And the way they want to set up the working methodologies, that maybe all scientists are not available every day. So maybe on some day only 1 or 2 scientists can come, etc. But because there are 5 of them, they decided the policy that at least majority of the people should be present to open that safe. Okay, so out of 5, if only 2 scientists are present, they should not be able to open the safe. But if 3 scientists are present, they can open the safe. So basically, that whatever that safe is, right, that has multiple locks. So that whatever safe, and with my whatever diagram I can draw. So that this is lock 1, lock 2, etc. So like there are multiple such locks. Okay, and then each lock, I mean, we can make duplicate keys of each such lock, and then the scientists are there, A1, A2, A3, A4, A5. Each scientist will receive a combination of few keys. So maybe the first scientist will only receive these 2 keys. The second scientist may receive a different combination like that. So your question is to design this kind of pattern of assignment so that now do you see how this relates to the question? Because if any 2 scientists are present, let's say A1 union A2, which means all the keys A1 has along with all the keys A2 has should not be sufficient to open the safe. So it is not equal to the full universal set. But anytime 3 scientists are present, they should be able to open. In fact, within them, they may have some extra keys, like duplicate keys, doesn't matter, but together they can always open the safe. Okay, so this is the real world motivation of this problem. And you can actually try to generalize this. Here we are talking with 5 scientists, but in general, if you have a very large number of scientists, some odd number, and then what is the policy they have to, how will they assign the keys for that? So that is what the motivation of this question is. Okay, so then now coming to how this is related to question 3. Just looking at the condition, okay, let's forget the rest of the problem. But the first condition here, each pair of distinct subsets AI AJ satisfies AI intersection AJ is non-empty. And now here it's AI union AJ is not the full set. So the principle of duality, right? This is a very important idea in logic. So the theory of logic is what I'm saying. That there exists a one-to-one correspondence between these operations. So wherever you have intersection, you can replace it in, or wherever you union, you can replace it with multiplication. Wherever you have an empty set, you can replace it with your full set. Wherever you have the full set, you can replace it with the empty set. So whenever you apply the complementation, which is sometimes known as the dash operation, right? Wherever the complementation happens, these elements can be swapped one for one, and you can convert one valid theorem into another valid theorem. Okay? So this kind of a duality exists, something that we have also seen before in other examples. So this is very useful here. So for example, just to give an example of how this can be applied, let's say we have some. Let's take our inclusion exclusion principle, right? Or not, but let us take a statement such as this: A union B intersection A union C. So let me draw the diagram. So when I say A union B, I am talking about this whole region. And when I say A union C, I am talking about this. So the region which is common to both of them
A union B intersection C.
A union B intersection C. Yes, correct. Because basically entire A is present. And this part is present. So this is in a way, this is like, you can see this is like a distributive law where you had this is, you can see, it's like if I had AB plus AC is equal to A times B plus C. It's almost like that, where you are able to pull this intersection sign, union sign out of the bracket and combine it into one, something like that. So now this is a valid statement. I think everybody can agree, at least looking at a diagram, that this seems to be valid. Now let us run it through the complementation principle, and let's assume some universal set which is surrounding this whole block. Okay, so if I just take the complement of the LHS, obviously complement of the LHS will be equal to complement of the RHS. But now when I apply the complement, let us reverse all the signs. So as I said, duality implies union becomes intersection and intersection becomes union. So the LHS will now read like A intersection B, A dash intersection B dash, union A dash intersection C dash is equal to A dash intersection B dash union C dash. Okay, so I term by term, I sort of propagated that complement operation inside the brackets. Okay. And when I do that, I end up with another valid result, which is this one. Okay. And you can check that now the regions that we're counting are exactly the region lying outside this blue line. So this blue line which I had shown earlier, right? So everything inside it was what was counted earlier. Now the region we are counted is exactly everything that is outside. So this part. But both LHS and RHS are counting that exact same region. Okay, so this is the complementation approach. In that spirit, now if you look at this condition, the first condition AI intersection AJ is non-empty. Right? So AI intersection AJ is non-empty. What if I take the complement of both AI and AJ? What I'll get is that AI dash intersection AJ union AJ dash will not be equal to the full set. So in other words, what we're suggesting is that whatever was the answer we found to question 3, the same AI AJ, if I just take the complement of every such set, then the first condition will be satisfied for the question 6 also. And same is happening here also. Here instead of 2 sets, we have 3 sets. And here the intersection is empty. Instead of that, we are saying the union is the full set. So let's just see if that is really happening. If we go back and look at our original definition of those 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So this was our original set S. And we said let A1, A2, A3, A4, A5. And we were making the ticks. So when we said that let A1, element 1 belong to set A1 and A2. So we made the ticks that way. Actually, I could have copy pasted from the previous part, but this is faster. Okay, so the ticks are how we are defining AI. But now let us define BI using black color. So now, so AIs were defined using the ticks, blue ticks. Let's define BI using the black crosses. So wherever I draw a cross, that element is included in BI. So B1 set B1 contains the elements 5, 6, 7, 8, 9, 10. B2 contains 2, 3, 4, 8, 9, 10, like that. Okay. And now let's erase the AIs just to make things easier to read. Okay. Now can you verify for yourself first that this set is solving the scientist problem? So the first scientist has the keys. This first row shows which keys the first scientist has. Second scientist has these keys. Third scientist has these keys, etc. So if any two scientists show up, let's say B1 and B4 shows up, together do they have all the keys to open the 10 locks? Which key is missing for B1 and B4?
Key 3.
Key 3 is missing, right? So key 3 is not present. But if any other person joins the party, let's say B5 also joins. So B1, B4, B5 together will have all the keys. Okay, so in that way, answer is satisfying the problem. Okay, so therefore, what we know is that 10. So here the question was how many elements should S have? Okay, so here we have 10 elements in S. So the log 1, log 2, log 10. So n is equal to 10 is certainly a possible answer. But the question is, we wanted to find the smallest possible. So why will n9 or anything smaller than 10 not work? So that is what I had not answered, but Arnav says he already has the solution. But just give me a couple of minutes to think if I am able to find it. And others can also think about this problem, that why will n less than 10 not work? Given that we have now showed the construction part. So I think this is where I'm thinking the duality extends into the proof as well. We already have a proof of question 3, right? So why don't we take the complement of that proof? If you remember in question 3, I had asked the question, how many sets AI can each element of S? So I had asked at most how many elements of, at most how many sets can each element of S be part of or belong to? And we got the answer as 2, because we saw that if any element belongs to 3 sets, then there is a problem. So if I just flip this question and now ask at least how many elements or at least how many sets BI can each element of S belong to? And
Not
I'll get
belong
the
to,
answer.
right?
Sorry?
It should be not belong to, right?
Yeah, sorry. Actually, we are taking the complement. cannot, right? No, sorry. I'm not, because I'm inverting the question, I don't need to invert this. I'm going to invert my answer. That is why, I mean, my answer is going to be 3 now. That's why I can keep it this. Can.
Okay, sir.
Or rather, instead of can, I should say must. That each element has to belong to 3 sets. At least 3 sets. Because what will happen? Suppose there exists some element in S such that J belongs to only 2 sets. Let's say J belongs to only A1 and A2. Okay, and J does not belong to A3, A4, A5. Now what will happen? The third condition says that if you take any 3 sets, their union should contain all the elements. But that will not happen right now because A1 and A2, A3, A4, A5 union will not contain J anymore. So therefore, J is forced to belong to at least 3 sets. Okay. But so J belongs to at least 3 sets. Along with that, what the first condition is saying is that AI union AJ is not the full set, which means for every such pair AI and AJ, again the complement. Previously, we had said that for every such pair, that common element which has to belong to both sets is the one-to-one correspondence. But now we are setting the reverse correspondence that AI union AJ, I mean, there exists some element X such that X does not belong to AI union A, right? So the one-to-one correspondence is now between this X and this pair. So if we are going to, there will be 5 choose 2, which is 10 such pairs, and therefore will require 10 such independent elements, where each element is the one which is excluded from that particular set. Therefore, the number of such elements has to be at least equal to 10. Okay. I'm not 100% confident about my proof yet, but at least in overall outline seems to be consistent with what we did before. But anyway, Arnav, what is your proof?
There are similar, like for every set of two sets, two
Okay.
subsets, there should exist at least one element which does not belong to both of them,
Right.
and that element should belong to the other 3.
Yes, that was important. So yeah, these Xi's are guaranteed to be distinct. That is what I was not sure.
Yes,
Yeah,
so
that-
because they are guaranteed to be distinct. That's why they get.
Correct. Yeah, that was the missing part. Because if some, let's say some 2 Xi are equal to each other, which means that no, then what happens? Then okay, then that means that Xi doesn't belong to 3 AIs. That we already showed that should not happen. Okay, fine. Okay, and in fact, I will encourage Raghav your approach, right? You had done some counting approach. Just see if that can also be taken in some way and translated into this problem.
Yes,
Because
that's
all
right.
the similarity would be possible, right?
That's what I'm trying to do.
Okay, sure. Yeah, but one way or the other, it's an interesting problem. And I mean, how to extend this pattern beyond 5 elements and find the smallest possible value of n every time. But you see how question 3 helped us to do question 6 very quickly. So, I mean, the point to be made is that it's always useful to find related problems. Don't just stop at one question. See how you can come up with other related questions and try to solve all of them together instead of solving every question in isolation. And whenever you have any set theory kind of notation, this complementation principle is always useful. In fact, there is a lot of similarity between this and what we call Boolean algebra. So Boolean algebra is a system, just as we have studied groups, rings, and fields in some way, that there are ways to generalize the patterns we see in natural numbers and things like that. So Boolean algebra is you can say the higher order study of set intersections, logic statements such as true or false kind of statements. All of them have like one-to-one correspondence through Boolean algebra, because in a way you can think of a set in 2 dimensions. First, it is just a collection of objects, but you can also think of it as a condition that let's say, we often write it that A is the set of all x such that x is less than 5. So this condition x is less than 5 is itself a statement which is either true or false. And now when you take another set B, which may have its own other condition, let's say y less than 2. So the condition y less than 2 becomes here. And now the operation of taking A union A intersection B, do you see that that set will correspond to the condition that the condition C1 and the condition C2 are both true. So basically the intersection symbol and the word and have one-to-one correspondence. The union symbol and the word or have one-to-one correspondence. And the empty set. So what is the empty set? Empty set is the condition that nothing is true. So empty set is the condition of falseness, like universal falseness. Your entire universal set can be considered as the set true. And the complementation operation is the word not. Okay, so all of them have like one-to-one correspondence across properties. And therefore, something that we wrote earlier, right? What was that expression? A union B intersection A union C. We will say that this is nothing but A union B intersection C. You can translate this word for word and get a valid logical statement which says that A or B, where A, B, C might be some predicates, doesn't matter. And A or C is the same as saying A or B and C. And you can check if this is true. That whether whatever are A, B, C expressions, it will be the case that A is true or B and C is true only if A or B and C is true and A or B and C. So it's very hard to say, but they will figure it out. Okay, anyway, that is a distraction. So we are done for today pretty much. So for next Sunday, I will send the problem sheet in advance, so you get a few days time to attempt it. But meanwhile, keep trying from various sources yourself. And even the questions we did today, if you work offline and find some new interesting solutions which we have not covered, then by all means do share it on the WhatsApp group. So we'll keep on taking this forward. Okay, I think that's all for
Sir,
today.
around when are the IOQM results declared?
Roughly, I think they expect it to be end of November or first week of December, but I don't know.
Okay.
Yeah. Anyway, we'll keep on working like to the best of our judgment, what we think is the result going to be, and work with that spirit. Okay, thank you.
Thank you, sir. Bye, sir.